we'll get started here. JB Poline from M&I will break down the sociological and statistical components of reproducibility for us. Take it away.
Thank you, Ariel. So that's the snowy M&I, and you're really welcome to visit whenever you want. That's my lab. I just want to thank the lab before I go on other things. This talk is a little bit of a, like a patchwork of things. I hope you'll enjoy at least some of those patches. And I will talk, first of all, a couple of stories that Russ hasn't, talked about that I would like to at least take a couple of examples that I think are interesting. Most of the talk and hopefully the interaction will be on basic statistics, and my goal is to first demystify some of those things, and secondly maybe unconfuse some of those things, and it's very basic, so I apologize to the to those that have like our statisticians, or like this is not for you, this is for like more the basic neuroscientists and that have done some statistics but like lightly, and then I will go on what can we do, and along the talk you'll see there is always some technical aspects, and there will be also some some more like a sociological or even a psychological aspect to the problem of reproducibility. I'd like to start with one example that wasn't taken yet. That was, I think probably one of the most prominent sort of things, and that happened. There was a paper in 2009 by Bagley and Combs. And Bagley and Combs are two biostatisticians, and they tried to reproduce the number of papers by Poline et al. And Poline et al. Had this great idea that you could choose some cell lines that are most sensitive to specific drugs, and then use the patient expression profile to predict which drug were going to be sensitive or not sensitive to a drug, to response. So that's a great idea, so the biologist and the medical school saw that paper and said, hey, we want to do that as well. So they went to the biostatistician and said, hey, can you help us implement that method? The method had a bit of an SVD, they have possible components, so it was not like a straightforward kind of a multiplication or addition kind of thing. So they tried to do this, and thanks God, there was the data were available, because there's some registry of cell lines and the data were available, so they could actually try to with the data to see what what was done in the actual paper. So and they tried for months, and basically for months they kind of tried to imagine. So they couldn't get the results, and they tried to imagine what kind of mistake could have been done such that I get the results that are published in the paper. And so they tried all the possible mistakes, and that's like complex, of course, because they are the tree can grow quickly, of course, okay. So eventually they managed to replicate the wrong results in that paper, okay. And then I think what I want to emphasize a little bit, the second part of the story, two things actually. One is that's later on, and if you look on the web, the Poline et al. Kind of scandal things. Later on, there was some attempt to cover up by the original authors of the mistake. But the original mistake was just a simple and okay mistake in some ways, right? And I think that most of the cases are not on the problem of reproducibility is not due to malpractice in science and people faking data and all those things. Most of it is actually just our practice of how we try to do science and sometimes don't manage to do it properly. So put apart the aspect of the aspect of like the original author trying to actually do some cover up. That's not the problem. The problem was what kind of mistake was done to arrive to the result. And the second problem is what happened to when Combe and Bagali tried to say to the journals and the community, hey, there's some problem with that analysis. So on the later point, they try to publish that, they call it the forensic analysis of that paper. They try to publish it in the original papers where Petit et al. Had published, and they basically couldn't. The Nature Neuroscience or Nature Medicine, all the things say, hey, no, that's that's not the kind of things we publish, or whatever was the editorial response. It was always like a no response to the thing, despite the fact that this was happening at the time when there was a clinical trial on actual patients with those results. Okay, so actual people being impacted. It's not always the case, right? In neuroimaging or neuroscience, it's not always the case that that you get actual people being impacted by a result, right? This was the case here, and despite that, journals were basically showing, hey, no, we don't publish that kind of thing. So yeah.
Sorry. So the journals that were rejecting on which level? So if it's the editors, then it's also researchers. So then they can become public competence.
I suppose so. I don't know. I haven't dig into who actually said no, and I don't think we have easy access to that information. I think the kind of the takeaway message is often at the editorial level, when Nature Neuroscience or medicine Nature Medicine or those kind of journals, when they see something a bit more low level technical things, and maybe not without the hype or the things, they tend to not take just say, hey, that's not for our audience, kind of thing. So finally they pushed it to a stats journal, it was another applied statistic, which is a good journal, but not mainstream kind of a medicine aspect, which was the audience that needed to be averted. And the editor said, hey, that's really important, let's publish it, and in 2 weeks it was published. So it's that's kind of also the culture. I mean, I want to point to the culture aspects on this publication story as well. So that's the Petit et al. What was the mistake? That's a very interesting story. The mistake was that there was at some stage a software that needed 2 arguments, on a command line, a software needed 2 arguments, 2 Excel spreadsheet or CSV type of file, one with the headers of the columns and one without the header of the columns. So obviously, a recipe for disaster. I mean, there's no check, of course. I mean, this is way back, and it's so easy to mess up with that. It's so easy to make that mistake. Which one is without the header, where probably the communication was very poor and all those things. And therefore, all the genes were kind of shifted by 1 line, and that's how the mistake happened. So they conclude, Bagali and Combe conclude, poor documentation, even well-meaning investigator may argue for drugs that are contraindicated to patients. So basically say, hey, and they say the most common errors are simple, like a row or column offset, things. And the most simple errors are also common in those fields. So that's an interesting story. I think I want again to emphasize that the fraud in science is really not, in my experience, prevalent. It's not. It's really like a honest mistake that we should target and think about. In another kind of area of science, which I thought was interesting because that was the one that triggered a lot of the reaction. There was this Peggy and Ellis, editorial in Nature saying, there was this little pharma that tried to take very high-profile papers with groundbreaking results. Yes, question.
Sorry. How do you define fraud? You said it's not prevalent, so I'm just curious what the definition of fraud is.
Well, fraud is really the intention of, I know that I'm making a mistake, I'm making something that is wrong, and I'm making it, unintentionally, right? Mistake is just it's unintentional. Yeah. So that little pharma, Amgen, looked at 50 papers that had like very interesting results for like preclinical cancer research, and they were all in the like very high impact journals, and they tried to work for a couple of years to reproduce those results. And basically, when they couldn't, they asked the authors for help. When the authors for help didn't work in their lab, they went to the author's lab to do like it's a lot of work to actually reproduce. And that's also a message. Like if you try to reproduce or replicate some paper somewhere, in many cases, it's going to be super hard work, and you're not going to be thanked for it. It's a so it's a part of the culture as well, the cultural problem that we have. But basically, in that specific case, they could replicate, like a fully 6 of these 53 results, and maybe another 20%, like a half, some of it, some of those results. And that really kind of was, I think, one of the, NIH really reacted to that at some stage, because they're thinking, okay, we are putting millions into those R1, grants, and the farmers that are actually creating jobs, and and those startups are like creating jobs. When they try to build on the top of that, they actually fail mostly. There's an interesting follow-up on that story, which is done by Brian Nosek. I think Brian Nosek is the last author of it. That basically tells the same kind of story with a bit more like nuances, which is it's basically the problem that in the papers there's not enough information. The paper is not something that you can take and work with to replicate at least an experiment in that field. And I think in neuroimaging, that's almost the case always. Like it's always the case almost. So that's that's 10 years later. But 10 years ago, like almost 10 years ago, there's the big NIH plan to say, hey, we have a problem. We need to enhance reproducibility, and they've done a bunch of things. I don't think, and I think Russ would agree as well. I believe. I don't think we have done some progress, and I think we should look at those progress with proudness, and we should be aware of those progress. I don't think there is a big like a cultural and shift in the paradigm of how we do science and how we do neuroscience and neuroimaging. I think it's been like more like slow, persistent progress, and I think we should definitely look at that and be happy with that. I don't think it has been like this cultural shift or this paradigm shift that many people would have hoped for. When I say many, that's the problem. I mean, not that many. Yeah. Anyways, so that was a kind of an introduction. I'm now going to be very boring and more like on the teaching side of things. Again, if you know those things, phase out, do your emails, like that's okay. But I want to dive into a little bit of the statistical aspects of some statistical aspect of reproducibility, and starting with a little bit more like a philosophical aspect. With saying that when you start to ask a question, to some data, following proper, like you should be able to actually falsify the theory that you have. Let's say you have a theory, you have like an idea of how things should work, and you should be, if you're doing some experiment, if the theory is like scientific, you should be able to falsify it, right? That's the Popperian kind of framework. I think we're still mostly in that Popperian framework, although it's not the only framework. So we need to falsify things. And what are our tools for falsification? And I would say, obviously, they're mostly like the usual, statistical test aspect. But then, what do you reject is the question that I want to put to the audience. And what null, like we know, but then rejecting the null. I believe that all of you know about that. What null should be rejected? So if I want to learn how traumatic brain injury affects brain connectivity, what do I need to reject? I mean, and that's an interesting question to maybe ask yourself time to time. Like, think of the framework of the theory that you have, and what kind of test are you doing to actually validate or invalidate that theory. And again, Popper would say you should try to invalidate it. And that's his framework. All right, so let's review our kind of a falsification tool a little bit. And the most prominent one still now, and there's been some evolution, but still is the null hypothesis testing framework. And before that, I just want to point to the vocabulary. I don't think that is a classic slide, so you may have seen it before. But I just want to say, when we talk about reproducibility versus replicability, we are usually talking about reproducible being the same data, the same software or analysis pipeline, while replication would be more like the same analysis pipeline, but a different cohort or different data set. And on the other side, if you're taking the same cohort and you're trying with a different method that should give you something roughly the same results, then that's where usually people talking about robustness. So that's one way of defining things. The right way of thinking about those things is really generalizability. On what axis do you axis do you generalize things? So it could be the axis of cohort. In that case, we're talking about replication. Could be the axis of software. In that case, we're talking about robustness. Could be both axes. It could be some other axis like time or like other acquisition parameters, whatever. But the question you have to ask yourself is on what is the dimension, what is the axis that I am pretty sure I'm generalizing on, like what I can generalize on. So that's a difficult question. It's practically impossible to look at all those axes. So we have to elicit take the ones that are important. So p-value, sorry about that, but they're still very prominent. They're very dominant. They're basically like software, whatever, and there's a couple of framework on which they think, but mostly we're using those things as in the Fisherian, sometimes in the Niemann-Person framework, which is more a decision-making aspect. So Niemann-Person is more like you make a decision with those things, while Fisher is more like okay, that's some indication of something on your data. So okay, so you all know that. So just repeating the obvious. We're trying to control for the type 1 error, for the false positive one, but there's also the type 2 error, which is a false negative problem, which is associated with power, which is 1 minus power. It's basically what's the chance of actually detecting something when it exists under the alternative. So I want you to take that read that sentence, which is very simple, and try to answer that little quiz. And feel free to so I think I have prepared something on Slack. If I go to Slack, and you should see the now on your Slack. That's actually showing the screen. So you should see that little thing. So let me put the slide back. And the question is, I've got two groups, one that has been treated with a drug and one without the drug. I look at some effect between the two groups. There's a difference that is significant with a p-value of less than 0.05. And H0 is there's no effect of the drug. H1 is that there is some effect of the drug. Please have a go and answer quickly that little quiz. What number will you put to those questions? Is it H0 is false, which one is true, which was probably false, and so on and so on. I give you 20 seconds, no more than 20 seconds, because you don't have to think deeply about those things. It's like when you read a paper, you're not going to think deeply about hey, that p-value is that, what does it mean? You just you read the paper and make some ideas in your mind with that p-value. So can I have a quick answer from everyone possible, or most of you? Nodding. Yeah, try not to be influenced by the, I know it's hard, it's impossible, but what is the sample size? I think it doesn't matter what the sample size is in that effect. You know, you have a p-value that is less than 0.05, and you know, and you have to kind of say what you think about that p-value. All right, I mean, I don't know if that sample is representative, but we we will believe that it is, and it's a common. So I mean, the kind of a most common answer is basically number 3, which is H0 is probably false, which always be bizarre to me because, you know, like if H0 is probably false, then maybe H1 is probably right? So why not 6 being the winner? Anyways, I think that reflects, you know, what happens in the mind of someone reading, you know, a paper and there's a p-value, and that's what, you know, like that is what, you know, the reader will think. The answer is none of the above. And it's you know, it's I guess you know, maybe you can feel it a bit of a trick, but it's not really a trick. Like the answer is not of the above because a p-value doesn't give you anything on the actual hypothesis. It's a statement on the data, and that's on the hypothesis, but doesn't give you anything on for the hypothesis itself. It's a statement of the data on the data. And that's something that is so easy to mess up, you know, like it's such an easy, like, you know, misinterpretation. And that's, you know, even like, you know, after I would say 30 years of statisticians saying, hey, don't interpret p-value this way, you know, this is still the same. And if you look at books, you know, psychology, for instance, there's the paper on the books in psychology, and most of them, 75% of them actually present the p-value the wrong way, and, you know, with the wrong interpretation. This is just to say, like, you know, our basic, very basic way of, you know, like saying something about data and things is often, I mean, it's still not very clear in our mind what it is, what we're talking about, and what we're, you know, and that's, I guess, it's a surprise that, you know, after so long, there's not, like, you know, this is not yet solved. And yet that is the case. I think that's also reflecting of the culture of science and the inertia of the training aspect and the inertia of universities. And I would say, and you will, you know, like I will talk a bit more like an inertia of a publishing aspect and all those things. And, you know, that was done on the medical students in some university, I can't remember. And you know, medical students will use those papers and tests to make medical decisions. So I think it is still important that we have a clear understanding of what we're talking about. So what the p-value is, the probability of observing a statistic equal or more extreme to the one seen in the data when the null hypothesis is true. That's the definition. So ponder on it. It's a probability of a statistic equal or more extreme when seen in data under the null. So it tells you something about the data, not about the hypothesis. If you want to tell something about the hypothesis, you have to go Bayesian. What is a statistic? Is the value of the observed of my first object a statistic? Can you raise your hand if you think yes? No hand raised. If you, okay. Yes, it is. A statistic is any function of the data. You've got some data, you've got some numbers, okay? Take a function, like, you know, those series of numbers, and that's a statistic. So often the mean, or like, you know, the t, which would be the mean divided by the standard deviation, all those things are usual statistics, but any function of the data can be a statistic, is a statistic, okay? So that's a definition of a, so you can apply p-value to so many things, but it's a very general kind of a framework. So you have to have the knowledge of the null hypothesis. That's a critical thing. You have to have the choice of the statistics, often again the mean or the difference of the mean, whatever. You have to have the concept that it's in the frequentist framework that, you know, you're repeating the whole study like in many ways, exactly the same kind of study, and this is what the probability is about here. I just want to quote Neyman and Pearson themselves, which were the ones that have actually made the p-value in the appropriate and solid statistical framework. They say we are inclined to think that as far as a particular hypothesis is concerned, no test based upon the theory of probability can by itself provide any valuable evidence of the truth or falsehood of a hypothesis. That's a very sobering thing, come on, those guys are the ones that are actually developing that framework, and they say, hey, don't use it to tell us about something which is true about the hypothesis. But I think it also speaks about the fact that, we are not making statements about hypothesis, we're making statements about data. So those are examples of hypothesis of distribution, and I just want to point to the fact that when the distributions are very different, like this is the gamma distribution, the statistic can be less than a very small thing and still have very different so p-value can be very generic and very general, and you have to be careful that they're not only applied on the normal distribution. P-value has a very interesting property, and for those maybe who knew about that? The p-values under the null are normally uniformly distributed. I'm sure Ariel knew. No, he didn't. It's a very interesting property. It's actually so under the null, your p-values are uniformly distributed. It's a very, and the reason is, if you read that, so I will upload the files. I don't think I want to go for the whole thing, but the reason is very it's kind of obvious when you read that carefully and when you let it sink. It's not that obvious to let it sink. If you think of the definition, what is the definition of a p-value? Then it becomes almost like a tautological aspect. Okay, that they are uniformly distributed under the number. The interesting aspect is that if you that fact has been used. You've heard in Ross's talk about p-hacking a little bit, right? And if I remember, I think he has talked about p-hacking. Anyways, maybe not. Maybe I'll go over that again. But the interesting thing, it can be used to do some testing actually, and of whether we are under the null as across many experiments, and I'll show you that. So the most common and serious error is to consider the p-value as the probability that the null is true. So that's a classic misunderstanding. And there's another thing which I think is kind of fun to actually go through once. So let's say you have you conduct some test with a type 1 error of 5%. You got some 80% of power, so the probability of detecting having the test being significant when the signal is 80%, and then and you do that with let's say for the testing of the true difference between the treatment, so two treatment compare. So how many true positive you would have? What's the percentage of true positive you would have having those two numbers, like 5% of a type 1 error and 80% power? Can someone who thinks there will be more than, let's say, 70% of true positive? No one? Really? Who thinks there will be less than 70% of true positive? No one either. Okay. So basically, you don't know, you don't want to answer. That's fine. But I would say that myself, if I was asked that question, I would say, okay, 70% true positive using those two numbers is probably likely. It's not far from the reality actually. But if you go through, let's say you have those 1,000, null hypothesis, you have 10%. I took actually 90% here. Oh, right. So I should have taken more. Anyways, so it's even worse. That in that situation is even worse. So you see that demonstration there. So you have those. So that's the sorry. In that data set, there is 10% of true positive. That's the reality. Okay, the reality is that you have 10% of true positive in the data set. That's what is the Now you have if you go through the numbers, so you've got 90% of true negative. I mean, the null hypothesis is true, and then you've got alpha equals 5%. Okay, so you have something like 855 non-significant results and 45 false positive. Okay, and then you put those false positive with the true positive, which is 80% of the actual true example, and that will give you 90 results. And then if you look at the 90, those combination of those significant results for the false positive and the true positive, then you have something like 64% of true positive in the results. So go through the path. Okay, so the actual true hypothesis, actual false hypothesis, not that are true, that are actually so the 10% of actual result of actual H1 are true, and 90% of H0 is true, and then go through what is your test and your power doing those two situations. Okay, and then you see that the true positive, the rate of true positive, the ratio, the percentage of true positive is 64%. 2/3, it's not too bad. It still leaves something like a third, okay, a third of the results that are that are wrong. So I guess to me that's not super intuitive. Like we're conducting tests and it's not really intuitive that we have that amount of true positive and therefore false positive. All right, so p-value can indicate incompatible data with the statistical model. Do not measure the probability of a hypothesis. We've seen that, and the scientific conclusion, clinical conclusion, should not be based on those values. And if you really want to do, like a proper inference, you really have to report everything. That's another problem that is being done, that not everything is reported. There's also the fact that this is not a measure of an actual interesting effect. So it's just a statistical test, but it's not measure of the effect, of the importance of the effect. And it doesn't give you a good measure of evidence regarding model or hypothesis. So all those things are, I think, to be reminded. So p-hacking is done usually with some very kind of I would say, it's something that you would do with being fully honest and without any fraud aspect to it. It's basically, I've got that data set. I have this idea of the hypothesis of the kind of thing I want to test. It doesn't seem to be giving me a good p-value that less than 0.5. Maybe I forgot a covariate. Maybe there is some part of the data that are kind of not really should not be in the cohort. Maybe there is another model that will be more sensitive. So I'm trying all those things, and at the end of the day, I do find a significant p-value. Okay, less than 0.5, and then I stop, and then I say, okay, now I can publish. So that's p-hacking, because on the way, you've tried many things. You've tried, different models. You've tried to remove some of the data. You've tried to incorporate some covariates, remove some covariates. Okay, maybe there was an interaction. I should put that in the model. All those things. That's a very natural thing to do, especially if you have spent months acquiring data, and you really need to have, basically there's a pressure, an academic pressure to find something in those data that is interesting and that can be published. Okay, so the problem, of course, is that so Simmons and Sons had this great idea. They looked at the literature and they looked at how data were analyzed in psychology, usually ANOVA kind of methods and practices. And they said, okay, we're going to take all those practices, okay, and then we're going to generate null data and analyze the null data with those practices, okay. And they find out that with all those practices that were published in the method in the literature, they had very much inflated type 1 error. On the null data, they would find not 5%, they would find sometimes 10, sometimes 20, sometimes even with some practices, 50% of false positive. Okay, so that's a problem. And there's actually some of us actually went through and say, okay, we actually have, using the fact that the p-value on the null is uniformly distributed, we can actually test in the literature, if you look at all the p-values, whether they come from a null or they are actually closer to the 5% value. And they found out that there is in some area of science, so there's a test, the statistical test that tells you, okay, here, if you find those distribution of p-values, you have a good chance that the community in that scientific field is actually doing some p-hacking. And that's basically whenever the distribution of the p-value is much higher for the things that are close to 5%, because if you have some effect, the distribution of the p-value should be kind of going the other way. So they have a chi-square test to say, okay, let's test the distribution of those p-values, and that tells us whether that field is actually doing something hacking. So it's a fun aspect, and actually not used very much, but so what's the recipe for how do you curb for that problem? And the easy way to do it is pre-registration. You tell exactly what you're going to do and how you're going to do in a pre-registration. You can't actually play with the model, play with the data. You have the recipe that exactly how you want to do things, and that's actually, even if you don't publish that pre-registration, that's an excellent way of actually thinking over what you're going to do and not kind of doing some p-hacking. And p-hacking could also be like a pipeline hacking in some stage. You're trying many pipelines of different processing or things like that until you find something. So I think that's there was some of a solution to the problem. Actually, some serious people said, okay, we don't want to see a p-value anymore in the literature. There are journals that have actually banned p-values, so you can't actually write p-value in your paper. It was a fun kind of a thing to see, in the. But obviously, what you have to do is, publish with all the full-fledged information, like not only the p-value, the confidence interval, credible intervals, if you have some, effect size, all those other data, because the p-value doesn't reduces too much the information and doesn't allow you to actually interpret things correctly. All right, so I've talked about p-hacking, a bit of how it can be detected. I want to talk about the 5-drawer effect. It's connected to some extent. So it's an old problem, 1997. And the problem is that we don't know how to publish properly null results, and that's a difficult. It'd be amazing if every experiment that we do have some significant results and have we are so good in theory that our questions are so little in some ways that we always know that there's going to be something significant, right? So most journals will ask for something which is novel and that is statistically significant and all those things. And therefore, if your study doesn't show that, then you are in trouble unless you have pre-registered. And therefore, the registration has been reviewed. And whatever is the result, you're going to publish the result, even null results. Okay. And this is the Z distribution in the literature from Medline. And I think everyone can see what's going on here. Okay, so there is a part of the distribution that we don't see. It must exist. It's not very difficult to think of what kind of curve should be on the top of this one, but that's not what is published. Okay, So what you see in the literature is probably a very small part of what is actually existing, and you don't see all those Z values or P values that are like, that are in the middle, and that's a huge effect, I think, and that's a huge effect that is super hard to correct, and it's really hard to actually fight against. And prioritization is one of the tools, but it's still very little progress in a long time. Okay, so yeah, prioritization again. Yes, Arya.
About that distribution. So I understand why there are peaks that around -2 and 2, but why is it so positive? Why is it so skewed to positive?
Because I think authors tend to ask the questions in a way that the resulting value is positive. That distribution should be symmetric. Like, it's just the same. You're asking whether group A is greater than group B. You could ask whether group B is greater than group A, right? And it just happens to be that most of the experiment or things are thought such that the result is a positive one.
By like a factor of 3. It's very good.
I know. That's very good. Yeah, I asked myself that question. I'm not sure I have a good, very exact answer to it. But yeah. But definitely a fun distribution to look at, and again, just to realize what's going on. And it's I think still having seen that distribution, we will still read the literature, but the same way we read it today. There's something in our brains that doesn't seem to be wanting to change or wanting to actually accept some of those things easily. That's a very interesting aspect to think about. All right, so one caution and aspect, I've said, null results should be published so that we have a good sense of what are the results, the true results. They should be published if they are well powered. If there is enough data that publishing a null result, publishing a null result with 15 subjects doesn't mean anything, or in general, because you have very little chance to find an effect that is, unless the effect is super large, right? So the power has to be enough with respect to effect size of the field to actually have some reasonable publication of a null result. And that's what reviewers, they are competent, will ask you of pre-registration. They would say, hey, you have an idea of what kind of effect you're looking at, you would look for, and how much data you need to show that effect. And if there is a null result with that framework, then yes, it's meaningful because you had enough power to detect something. Just again, basic stuff for the vocabulary aspect and the Wiener's curse. It's related, everything is kind of related, but not exactly the same thing. So that's why I want to put all the terminology in your mind. So what is the Wiener's curse? Is the fact that when there's an association that is passing a predefined threshold, so like for instance, when we're doing a p-value, a test, a statistical test, then the statistical effect, tend to be overestimated. So the size of the effect would be overestimated. That's a very basic, stupid thing. You're looking at only things that are above a certain threshold, and therefore, yes, you're going to, for sure, you're going to overestimate, because because you're going to look at only that is what's above some threshold. So that's a very stupid, almost tautological aspect, but it means that most of the effect that we see in the literature are overestimated. So when does it occur? Whenever there's a predefined threshold, so 5% is a predefined threshold, you're looking at effects that are above z equal 2 or something. Small sample sizes is one of the things where the effect is very variable, and therefore with a threshold you will overestimate. You've seen those plots probably. And when there's a very stringent threshold, which is interesting because we often do multiple comparison in neuroimaging, and therefore we have or in genetic we we heard this yesterday. It was a 10 to the minus 8 kind of a p-value, right? That means that anything that is less than that threshold will not be reported, and so the effects that we are seeing are really overestimated. So the more stringent the threshold, the higher the overestimation. And that's kind of a the classical experiment to show that. I don't have a printer, I don't think. But basically, the prints you see the diagonal, the one-to-one line is those are replication of 100 experiments in psychology, like mostly reaction times by NeuroHack. That's actually led to the open science framework development, this experiment. And basically what you see is that all those points that are under the diagonal have an effect that is less than the original effect reported. So it's the original effect on the x-axis, the replication effect on the y-axis. So this, the effects that the original effect of all those 100 experiments were probably overestimated by a factor of 50% or something of that kind. It gets complicated because you can think, okay, so in red and green, is it green or blue? I'm sorry, I'm colorblind. I think it's green. You have in green the ones that still have after replication a statistical p-value, a significant p-value, and in red a non-significant p-value. And the kind of original paper was saying, hey, those red things, the experiment, they were not replicated because they were not significant, at 5%. It gets complicated because if you look at, actually the good question would be, is my original effect size compatible with my secondly assessed effect size, like a replicated effect size? And you could say, okay, is the difference of the effect sizes between original and replication, is that difference significant or not? And actually, in most of the cases, it's not significant. And we basically saying like, there is not enough power in the replication to know whether those things were actually different or not. So it gets, it merges a bit the thing. I think the original result is still interesting. I think it stands that the effect size was overestimated in the original studies. It's still not proven statistically that that is correct. And there's ways of estimating the bias. If you have an actual effect size that is called D, depending on the number of samples, the power of your analysis, and the variance of the data, you have a formula. And if you think that your data are normally distributed, you have a close form formula to actually know what is the bias. So what is interesting, and that slide is not to scare you off, it's just to say that it depends on the power, and the greater the power, the smaller the bias. Okay, so that's you should know that. Okay, how am I doing with time? All right. Effect sizes. I want to say a word on effect sizes because we talk about effect sizes. I want to take the most common and most stupid effect size, which is the difference between two means of two groups. That's the raw effect size. That's the first one. Then I'm sure that some of you have heard that the Cohen's d or the G effect size or many other things. Many of those things are just the same thing, but divided by some measure of the variability of the data. So I just want to put that in your mind again. So if you think of Cohen's d, it's basically some, let's say, difference between two means, and it could be something else, but standardized by the standard deviation of the data. And the thing that is associated in one-to-one mapping with the p-value is the z statistic, which is standardized by the standard deviation of the means. So that z thing has the square root of n that you all know about, right? So I just want to make sure that you've seen the z, which is we have the the sample size in it, okay, which is the same thing for the p-value. There's a one-to-one mapping again between those two things, and the standardized effect size, which hasn't got the sample size in it, okay. So the Cohen's d is interesting because of that, and you should always report Cohen's d or G or other things because of that the difference. There's too many parameters in that z value to make it interpretable easily. That's the thing. So what's an effect size? It's basically anything, but what is a good quality of an effect size? It should be simple. If you put an effect size that is the, I don't know, a function of those eigenvalues that are, whatever, it's not going to be easily interpretable. So like a simplicity is definitely quality for an effect size, interpretability, and if possible with units, or if you think of what kind of units that thing has. And as much as you can, standard in your field of science, which is, that do not invent yet another effect size or try to relate it to something that's exists. So percentage of variance, correlation, of course, all those things. It's hard. I sometimes read a paper and say, okay, what's the effect size? I would say most half the time it's impossible to see or to find, and you're thinking, okay, I don't know what's the effect size. It's really hard to to know. It's hard to change the culture of the reviewers, and there's been many kind of recommendations and of practices for reviewing and reporting all those things, and still I think it's getting better, but the progress again is very slow. I wanted to take this example just to give you the sense that if you those things that I've talked about are mostly very simple mathematics and statistics, right? They're not they are very clever things. I want to give you a sense that you can actually with some simple tools get to those effect size, and have a feeling of what's going on in a paper. So I took that example, and it's a very old example, but it doesn't matter, which reported, so it's interesting. So it was the fact that subject with one allele of the serotonin transporter, when they are looking at the fearful faces, had more or less activation in the amygdala. Compared to the group that has another allele of the short allele of the long allele of the serotonin transporter. So it's interesting paper. The amazing thing in that paper, it's a very old paper, 2002. Amazing thing, they actually replicated the results, and they said they had one. So at the time, 15 subjects was entirely acceptable. They had 15 subjects. But they said, okay, we're replicating on another 15 subjects. Okay, 14 subjects. So we replicated the results. And I was wondering, so actually 14 subjects each. So they report the mean of group 1, the mean of group 2, the standard deviation of the mean of group 1, and the standard deviation of the mean of group 2, and the sample size. So those are the three values times 2, but that you have to play with, and you're thinking, okay, what is actually what actually is the effect size? Does anyone would feel comfortable in saying, okay, give me 5 minutes and a piece of paper and a pen, and I will find that for you? Can someone who thinks that is someone that you think is feasible? Yes, 1, 2, 3, 4, 5. That's cool. That's really good, because that's, I think, I hope that with a little bit of work, every one of you should be able to say, hey, yeah, I can see how I can do that. I think if you've done it once, it's much easier to kind of build on that. So I'm going to do it for you. So I'm going to start with the standard deviation of the means. I know that the standard deviation of the data is related with the square root of the sample size minus 1. Okay, so that's an easy one. I also know how to combine 2 standard deviation of data in one. Okay, that's an easy thing to do. Now I have I actually know now what is the standard deviation of the data across the 2 groups. I've combined those 2 sigma, okay, and I can go to the Cohen's d effect size. But, I've got a coincident effect size of 1.05. That's already, you have an information that is, you're thinking, okay, I know that effect size of 1 is super high. Whether, the activation in the amygdala, when you have the long allele of the serotonin transporter is going to give you an effect size of 1 it's a question that you can start to think about, like the plausibility, the biological plausibility of those things, okay? And that's what effect size is about, right? It's about the biological plausibility. So now I was asking myself, what's the percentage of variance explained by this thing, right? So that's actually not difficult at all. You can write the estimated model, which is just the average and the difference of the means, and then the residuals, and then you do that computation. Because you have all those numbers, you can compute the percentage of the variance explained, and that's about 40%. So 40% of the bold signal explained by this serotonin transporter, I think it's super high. And I think to me, at least, I would read that paper with caution, or at least I'm thinking, okay, if that has to be replicated, maybe it will replicate, but probably with a much smaller effect size. But those computations are simple. I mean, it can be done on the back of the envelope easily if you have the basic tools and the basic information that you now have. So I would encourage to whenever there's a paper, you think, okay, what's the biological plausibility of that? Try to do those things by yourself. There's another issue which I just want to mention briefly, which is what if we have the UK biobank? What if we have ABCD or 10,000 subjects, 50,000 subjects? Then the other problem is that you may find some very large number of significant tests. Everything is starting to be significant because the minute effect is going to be significant, statistically significant. And this is where you have to think, what is the biological significance rather than statistical significance? And so it's particularly important in medicine, of course, when you have to think about the biology and the patients. I'm going to skip over that thing. I haven't stopped to ask if there are questions. Suppose you will raise your hand or your voice if there is. If there are, but any questions so far? No? Okay. I was hoping for a question to get my attention. All right, a quick recall of power, because I've talked about power without introducing, like making sure that I was kind of motivating it before introducing it. You probably know that slide, so I won't go again to it, but power is that, in that simple case, the probability of having a test significant, which is everything on the right side of this red line, under the alternative. So power is really the key thing, because if you don't have good power, the study is not worth doing it. That's the first thing, because you are going to waste those 15 or 20 subjects because you have very little chance to find anything, that thing. And secondly, because without power, the results are going to be doubtful. Even if you find something significant, which you have no probability of doing, you will have results that are going to be unreliable. And I'm going to show you that with what is called the positive predictive value that you've been introduced to in Russ's talk. Power is hard, very hard actually sometimes to measure, because you have to know H0, you have to know H1, and therefore you have to know the effect size, you have to know some of variation, and you seem to have to know a lot of things that you don't know before you can actually try to estimate power. The answer to that is, despite the fact that you don't know those things, try to get best estimates and try to see, okay, if my effect size is roughly this, or is between this and this, what is going to be the number of subjects that I need? If I, those exercises, again, back to the envelope kind of exercise, are super useful to give you a sense. better than just reading that paper has been published with n subjects, and therefore I should take n subject because that's some kind of effect size that we're like. So it's that kind of assessment which is hard, but is really fruitful to do before you do the experiment. And you've seen that slide. Actually, there's almost like a perfect replication of that slide in another paper. So the slide where you see the effect size on the left, on the y-axis, and the year of publication with the size of the cohort on the left between the and you see how the effect sizes with the greater power and therefore larger cohort is decreasing. And again, same thing with the Marek paper. With small effect sizes are shown on the structure and function correlation with cognitive abilities or psychopathology, as well as the important aspect in that figure that if you look at the variation of those effect sizes for, let's say, a cohort of 150 subjects, for instance, which is already a large cohort, the variation of those effect sizes is very high, and that's what is I think even is important to have in your brain. It's not only the size of the effect; it's also how it varies with the number of subjects or number of samples. And you've seen that as well, which is a prediction accuracy with increasing sample size from Gael, that showing that predicting accuracy is decreasing with the sample size. So, how much time do we have? Yeah, I still have a bit of time. Positive predicting value. That's such an interesting and fun number that is also one of those numbers that is impossible to get at, and still would like to present it to you. Again, coming from John Ioannidis, and that seminal paper which says why most published research findings are false. And positive predicting value being the probability that the alternative hypothesis is true, knowing that the test is significant. So I have a significant test. Is actually my alternative hypothesis true or not? Okay, and what is the probability of that? So first of all, it's a bit of it's a change of paradigm compared to the classical statistics, because you have to make hypotheses probabilistic things, right? So you have to make those, and probability are confusing. Probabilities are confusing. There is the objective physical property of the nature of the system, which is like a let's say like a randomness that you have in a gas, or like a which is often it's one way of thinking about probability. Okay, there's the degree of belief that's called like evidential probability. There's the probability as the limit of frequency across random trials. That is the classical way we're thinking of it, especially in the t-test or a p-value kind of a framework, null hypothesis testing framework, which is like if I repeat that experiment a million times in exactly the same conditions, what is the limit of that? What's the probability of the limit, and that limit is the probability. And then there's a Bayesian framework that says it's a reasonable expectation representing a state of knowledge. It's actually that formula that I give, which is a very well-known formula, which is probability of A and B. It's probability of A times probability of B knowing A, or the opposite, probability of B times probability of A knowing B. That formula is part of actually the definition. So it's not like this is not a theorem. Most of the time, it's not something that is derived. It's a part of the definition of the probability. So you have to think of the probability is something that is like that, rather than because it's probability, it's going to follow that pattern. So probabilities are confusing. Still, the kind of the Bayesian framework has been shown to be much more consistent and mathematically consistent than the frequentist framework. So just for you to know, if there is a framework that we should invest into, it's probably more the Bayesian one than the frequentist one, which has been shown to be inconsistent. So PPV, again, the probability of the alternative hypothesis to be true, knowing that the test is significant, So is it worth concluding anything if this number is small? I would say that's probably not. And it depends on a number of things. And I want to demystify how you compute PPV and why it depends on those things. Because again, that's kind of like you may scare some of you, but it's actually quite basic or not too hard, formulas if you go slowly from one to the other. So let's try to demystify. So this is the Bayesian theorem. So I assume that you all know about that. So the probability of hypothesis H and D. That's what I've just shown you. So it's just like rewriting those things in different way, but it's a very standard result, and I believe all of you have seen the Bayesian theorem, and I've seen that formula quite many times already. So that's why I'm not going through that. So let's take the probability of the statistics, test statistic to be significant. So that's P of TS, and then you can divide it into the one that is under the null and the one that is under the alternative. So that's the first kind of addition there. And then you rewrite that using Bayes, and that's the second line. And so far I've done nothing, right? I've just written that probability. Now, if you look at the PPV, that's the probability of the alternative being true, knowing that the test is significant. So that's the Bayesian formulation of that probability. So that's easy. Now you just plug what I've just told you about. So you just plug the denominator with the line, and then you define what is the probability of the test significant knowing that the alternative is true. That's power. Okay, that's exactly the definition of power. And then you just rewrite that and using power, and you've got your result. So you got the last little bit that I did was to transform probability of HA divided by probability of H0 to be the odd ratio. So R is that division. So see, in 3 lines with extremely basic things, you have derived the PPV. Now, if you go to John Ioannidis' paper, I dare any one of you to actually understand what is the PPV and how you derive it from that paper. It's super hard. I mean, I found it very hard. I don't know, maybe some of you are clever than me and you find it easy. But there's for those things, I would say there's most of the time there's a very simple formulation and things that gives you some intuition that is better than the complex kind of framework in which often they are described. So look at that latest formula. So we got power on the numerator, and you got WR, which is R being the odd ratio, the probability of the alternative divided probability of the null. So it gives you that odd ratio is telling you how likely is basically compared to the null my alternative. Is it a hypothesis that is a bit crazy and I've got very little chance that it is true in general, or is it a hypothesis that I'm very confident about? And it's most likely to be true, and compared to the null. So I think that's the odd ratio, and then you multiply that by power, and then on the denominator you have alpha. So you see, you start to get a sense of what is PPV without too much. It's getting easier. There's only if you take that multiplication on the top, there's only 2 values really to play with. Okay. So, if you plug in some reasonable numbers, so like an odd ratio of 20%, for instance, which is okay, that's very likely but not very unlikely alternative. And then you look at power on the x-axis and PPV on the y-axis. You see that for a power of, let's say, 0.8, you have something almost like PPV of 0.8 as well, which is with alpha equal 0.05. Now, the problem is that power of 0.8, 80% power is very rare. We've seen in the Button et al. Paper and the other papers that you've seen on Monday. And also the p-hacking aspect is coming in, and 5% is probably unlikely as well. So you have 2 problems. Power is getting small, and with p-hacking you have more the type 1 error is probably more than 5%. So in that case, with let's say, I don't know, 50% power, and that p-hacking, which is, is not unreasonable, you got only 1/4 of a chance that the hypothesis is actually true, even if your test is actually significant. So that's again give you like a sense of the problem that you may see in the literature with those things. And I just want to relate PPV in another world, which is the machine learning world. PPV is actually prediction. So it's anyway. So you can look at a way of relating these two things with the number of true positive and number of false positive as well. All right, I'll skip this thing. It's hard to estimate well PPV because you need power. You don't know how to compute power. You need the odds. You don't know how to estimate the odds, and you need a tap error. So let's say that one you can think at least. But those two things are really hard to estimate. So how useful is that number? I think, again, it's more like a mental simulation of things, and that I think is worth doing, but taken with caution. All right. And the last point before I move to the conclusion of that talk is the statistical generalizability. There's a bunch of Tal used to co-organize this NeuroHackademy summer school, was the one showing that there's a lot of effects that are modeled as fixed effects in experiments that should be modeled as random effects. And then if you do like that modeling at the fixed effect rather than the random effect, you find inconsistent results, and you find that results are much more significant than they should be. And I will leave you to read the paper where I should have put the reference. That's basically look at the kind of modeling that is being done, because if it's an effect that should be a random effect, such as stimulus, for instance, stimulus. You're choosing one stimulus amongst many possible stimulus. Like you're showing a bird, or you're showing like like presenting a sentence. There's that sentence is taken from a pool of like many other sentences, or that bird image is taken from a pool of many other bird images, and those things should probably be random rather than fixed. So that effect, that problem, is creeping in many results. Right. So I've talked about small power, which is going to bias the effect size. The winner curse is also going to inflate effect sizes. The p-hacking, which is problematic for the uncontrolled type 1 error. And the Fadro effect, again, biases the effect sizes in the literature. I want to take one example of a study that we did. So we had that meta-analysis of the involvement of the cerebellum in essential tremor. So we took that meta-analysis, we did a pre-registration with a much larger, so we did some power computation with what we could see in the literature. We created a cohort of control that was much larger, and we tried to do like several analytical pipelines. We pre-registered all those things. And at the end of the day, we couldn't find anything consistent as the involvement of the cerebellum in the essential tremor. And I think mostly because a large number of the articles that were in the meta-analysis, the original meta-analysis, were actually with a very small number of subjects, or clinical population of 20 subjects. And I think that meta-analysis showed some results. But maybe some p-hacking aspect, maybe there's some inflated effect. But if you power sufficiently the thing, we actually couldn't find the results again, or not definitely not consistent across pipelines. There are ways of first of all estimating the effect size problems, and there's also ways of correcting the effect size problem. So that's one paper. You have the slides, so you can look at those papers. They're usually kind of what they call funnel plots, where like you look at the standard error on the on the y-axis, and be careful that the standard error in the other direction. So the large standard errors are the bottom, and the smaller standard errors are on the top. And you look at the effect size on the x-axis, and when you have like that discrepancy of the third plot, you can assess that there is some overestimation of the effect sizes. And there are ways of trying to correct for that by recreating some kind of a symmetric aspect to that plot. It's a complex literature. This one is actually not very recommended anymore. It's hard to do. It's it's a bit more like an art than a science, I would say. Sometimes it feels like it, at least. But I think it's a set of tools that are still underdeveloped in our own field of neuroimaging, and I think that's a direction that would be interesting to take for the future. I want to come back, since I'm running to come back to the original question. Some literature is showing that TBI is inducing a decrease in connectivity compared to the normal control group. So to advance science, I should try to reject that the TBI connectivity is the same as the normal control group, but the theory is not that is the same. The theory is that the TBI is influencing the connectivity differently than on the control group. So I should try to reject the opposite thing, which is is a TBI connectivity different from the normal control group? That's the thing I should try to reject. So that framework is almost never taken, and it's something I would like to leave you to think about, in terms of the theory that you're testing, and what kind of what thing you should be trying to reject with those statistical tests. So, yeah, in many instances, that's not the kind of the way things are framed. So there's a way that there are more general hypotheses that are interesting to reject. So, for instance, at least you should try to not to reject very narrow nuls. So the effect, the very narrow null is like, group A has exactly the same mean as group B, right? That's a very, very narrow null. Okay. So it's kind of easy to reject, because if you have power, at least, because, anything, there's no mass there. There's so better hypothesis is saying, hey, what is the interesting effect? And I should try to reject maybe whether that effect is, is within the minus, outside the -3 to 0.3, -0.3 to -2.3, for instance. So you see, like, you're trying to reject something that has more biological value. That's a better hypothesis to reject. Right. I will finish with some kind of thoughts on the, I would say, culture and sometimes even psychology. So we're still in academia in a place where success and promotions and all those things are very much defined by the articles that you publish. I think that's still the case, and that narratives are so important for those articles. You need to frame things in a way that reader would say, "Hey, that's a good story." And almost. I'm taking the word story with like in quotes, but I think it's sometimes you would hear someone say that, right? Other objects of research, software, library packages, educational material, data sets, even standards, may have a lot of impact on actual science progress, and but much less recognition in our academic world. So, oh, you don't see the title. It's okay. I think I was inspired by Ted Satterwhite that was saying that open science has 3 different things that are against it: time and fear. I actually said 2: time and fear, and actually adding culture to that point. So time and fear and culture are probably the things that are preventing kind of the open science to blossom. And open science itself should be, eventually, hopefully in the future, like just science. So time is the usual story that you have to have 3 papers for your PhD. What do? Do you do the third paper, or do you do the package that goes with the method that you've developed? That's time. That's the problem. And the answer is obviously you want to graduate and you do the fear. There's a lot of data scooping fear, and I've seen even in my lab students saying, hey, this code is so crappy, my code is so crappy, by the way. I just don't want to put it on the web because people will have a judgmental view of that and say, oh, that's it's human and normal, but it's still something that prevents the advance of open science for sure. And to some extent, pre-registration, if you think of pre-registration, you could think of pre-registration as a way to protecting yourself of putting the ideas that you have in the open already, such that they're going to be attributed to you, or if they're not, it's going to be easy to say, hey, I had that pre-registration an idea before, please cite cite this. Culture is complex. It's a big word, but I've seen a very different kind of mindset in biology and medicine versus engineering and technical work. I don't know if others in that room have also felt that same difference. But I think the engineering culture or the technical culture is often, I would say, saner and better in terms of open science. I don't know if that's and there's a lot of there's kind of a jungling between competition and collaboration in academia, but definitely there are places where collaboration are much more emphasized and competition less. There's one aspect that I always found very difficult to think about, which is the way, because the articles are so important, and because articles are referred to by the name of the first author in general. So this is the, for instance, amazing rocket metal paper. Okay, but suddenly someone says, "Oh, that rocket metal paper is flawed and it's really bad, for X reason." Okay, and then Ariel will not, but someone else will say, "Hey, I'm feeling attacked because this is my name that is being on the front of those things," and so the decoupling between a result and a work and the name, which is so personal to us, is not well done. So we should think of our result not being our results, our result being just results, and independently who they come from. And that kind of a perspective is hard to to take, but at least we can try. It's not going to work. I can tell you already, or not for everyone, but at least we can try to put ourselves in a position to say, let's say that wasn't my result. Let's say that was someone else's result. Would that feel the same? And would be and to some extent we should try to feel the same about that. It's looking at result in objectivity rather than being attached to a person. Misplaced incentive, so that's competition plus I would say culture of currency being the article has led to this paper was actually doing some simulation and showing that if you simulate labs that are doing good practices and bad practices, which ones are going to be successful, and it's an interesting simulation paper that is basically saying that there's a natural selection for bad science, which we should be aware and fight. I want to say something that is during that talk. I often refer to publishing aspect. I think publishing is really the thing that we should fix. That's I work on trying to do that, and not been very successful. But by expanding, first of all, what we publish and the recognition of all those research objects that are still hidden to some extent, that takes much time to create. So publishing is also a place where there's a huge business and money aspect. The reason is, so I really recommend that article. It's the long read from The Guardian. And they explain how Elsevier became like this amazingly rich and powerful kind of a company, right? So it takes the whole story of like the little societies, the royal societies, or little like societies in the world, like in the early 19th century, early 20th century, and late 19th, like and so those societies had those little journals, and they were printing themselves, like they were sending to printer, like and they were in charge of publishing, and they were deciding what they want to publish, and it was sometimes even not reviewed, whatever. And then there was like those clever guys came and say, okay, we're going to make money out of that. We're going to remove you from all the problem of that, handling that journal and those things, and we're going to do it for you. Okay, obviously for a fee, and then the problem became, and so they went into the conferences and the workshops, and when there was like symposium, they would approach the organizer of the symposium and say, hey, do you want to become the editor-in-chief of a journal? And obviously it's a recognition for the people, so they would be good for the career of that person to be like editor-in-chief of a journal and so on. So. And then of course they grow all that set of journals that were sometimes really good journals, and there are often very good journals, with the fact that with the new publishing means that we have, we don't much do like the printing aspect and thing. Setting up a journal on the web is very cheap. There are costs associated. I mean, they are real, but in general, when you don't pay the writers, when you don't pay the editors, when you don't pay the reviewers, when it's cheap to actually put things on the web, there's a fantastic business, and a lot of, and if you, the reason why you see like 10 new journals every day is because it's so it's a fantastic business. So yeah, I encourage you to read that long read. It's really worth doing. So there's a culture and business, academic culture and business interaction problem that I think is not yet, I think should be more in the awareness of the community. Yeah, and that leads to what, to like an increase in the number of papers, which is basically it's getting super hard. And what you do is you filter by the reputation of the journals or the reputation of the authors, which is really like a way of stifling things, because then it's hard to move that ecosystem anymore. There was some reaction. I don't know if you heard of the cost of knowledge. I actually signed the cost of knowledge. I said no, I'm not going to review for Elsevier. After Elsevier lobbied the Congress, the American Congress, to remove the free access to papers that were funded by NIH. So it was good to me. Like I had less papers to review. It was good. But it's not been super successful. I mean, it's been kind of successful a bit. Maybe some of you have heard of the NeuroImage Elsevier, NeuroImage Elsevier moving the whole editorial board to imaging neuroscience, and all those things. So there are some reactions, is what I'm saying. They're still kind of likely not the kind of mainstream thing. Like there's again no paradigm shift, more like a nudges, as Russ was saying. Cost. I think if we're talking about reproducibility, there are studies that are trying to assess the cost of irreproducible science. I would say, again, probably super hard to assess. At some stage, it doesn't matter. When you go to some numbers, like, this is like, 28 billion, whatever. It doesn't matter whether the number is correct or not. It's just huge. I think is the question. And same thing for the data. There was this paper that trying to assess the how much loss of fund is done with like unused data and unpublished data, and again, those numbers are probably wrong, but it doesn't really matter. Those numbers are big. Is the answer. And the thing is that this kind of a flurry of articles and journals and the things, they don't come with kind of like a faster scientific progress. It seems that they're actually ossifying things a bit more than they're actually making progress better. So that's one of the paper, like the Chu et al. Paper is saying. There are interesting conferences that are, if you happen to be able to go, like, Force 11 is an interesting conference about publishing and yeah, so what we probably need to do is, first of all, move the kind of a driving seat from companies that have a vested interest in making a lot of money, which is fine by itself, but when that is not very much aligned with the progress of science, then we have a problem. So, like, moving those drivers from companies to scientific communities, I think is one of the things that we should try to do. And then publish other objects with the same reputation as the kind of a story aspect. So data, software, things that training material and those things. I will. So I worked on the finally Aperture and now Aperture Neuro with OHBN. That's one of the things. There's the Neuroscience Journal Network of NCF that is interesting in that respect. There's some preprint. With NeuroLibre, Elizabeth actually worked a lot on it and did a fantastic job for, like, an AGA, also, like, on having a preprint that actually can rerun your Jupyter notebook and be reviewed technically for that. And trying to find ways of publishing all the details, meaning actually the code, the data, and things such that you know exactly what you mean when you have a sentence in the discussion saying, hey, this is what the conclusion of the paper is. You actually have the exact information about that sentence in the associated object. Right, so I think that's it for today for me. I think I would like to encourage everyone to invest also in both the technical and the governance aspects of fair data and fair research objects. Engage with communities. Everyone, each of us alone is not going to. That's not going to work. If we want to move the whole thing, we have to have, like, thousands of hands because it's a big thing to move. Contribute to the change of culture. Don't impose on yourself things that you won't be able to, like, carry on. We still need every one of you to be a successful scientist in the context where they live. So that's one aspect that don't take care of yourself and your career. And I think that's and think of incentives that are around, like, love because we love doing science, but there's also, like, for other, there's also money, fame, and rules, and those are incentives that are interesting to play, such that you can move the whole culture differently, a bit differently. Yeah, I think that's it. Thank you. Great.
Yeah, I have a question regarding power. I understand that it's important to estimate it if we can, but let's say I'm conducting an experiment, like I'm recording data, and it's some effect size I actually cannot, like, really assess until I have actual data. So would you say that it's important to first just pilot my study, just have some preliminary data, like see the effect size that could be going on, but then again I have the problem of sampling, that maybe the subjects that were part of my pilot study are, like, maybe biased in some way, may lead to bad conclusions. So how do I deal with this estimation of power?
That's a good question. It's a hard one. So the question is, how do we estimate power? Given that if I pilot things with a few subjects, I will have a bad estimation of the effect size. So how do I, do it? I would say, depending on what you can do. Okay, so if you, I would say a combination of literature review and initial sampling. Let's say, maybe in the Bayesian framework, where you can possibly say, hey, this is the primary kind of information that I have. I only have, and again, it's just a matter of fact that we will need more subjects in there. So whether those subjects should be burned by, with estimating, an early effect size or not, and how to maximize the reuse of those things. There are techniques to do it actually, to maximize the reuse without having circular thinking that things. So, it depends, but I would say a combination of those two things is probably the most reasonable answer. Yes.
Given the things you covered, p-value, generalizability, hacking, etc., Tony wrote a paper on the generalizability crisis, and he said after covering a number of things that you said here, that we should just do something else. What part of that do you agree with?
I think so. I should also always be careful when I give that talk, and I think it's something worse. There is a lot of good science being done. It's just like we think that there is also a lot of bad science, but given the number, there is also good studies and good science being done, and I think focusing on those and is one option and one strategy. So I don't think we need to do something else. We need to be careful in what we do, and again, more. I think it was I don't know if it was Ross or somebody else like saying, love the question you can answer rather than the answer the question you love. Is one aspect to that problem. But I definitely would try to avoid the too pessimistic kind of depressing only aspect of those things, because I think that's not true. Right? There are really cool work and interesting work and well-powered work and things that will replicate. And so I think that's focusing on those things and I would still think that if you want to contribute to pushing the culture in the right direction, be careful with the publishing aspect. I think that let's try to globally mend that aspect, because at the moment, because the journals post reputation and reputation is very long and hard to make, it's very hard to move that thing. So I think so trying to move that is the long term. That doesn't need to be for tomorrow, but it's the long term and aspect that I would love to see changing.